Alright, now let's have a look at question number 4, which is a question related to the topic moments. Let's see what it says. So it says here that a uniform rod has length 3 meters and weight W newtons. Okay, so first of all, it's important to note that it's a uniform rod. That means the weight of the rod will be acting right from the center. The rod is suspended by 2 light vertical ropes. All right, very important. One rope is attached to the rod at A and the other rope is attached to the rod at C. So here you can see that's rope 1, that's rope 2, where AC is equals to 2.1. All right, we can see that the rod is in equilibrium in a horizontal position as shown in figure 2. The tension in rope C is 350 newtons. So let's mark that. So tension, as we know, acting away from the object always. So that's 350 newton. Okay, show that W is equal to, and what's W? W is basically the weight of the rod. So we need to show that's equal to 490. Now a good idea would be, since we will have to use this probably for multiple parts, so I'm just going to take a picture of it. Okay, and I will paste it over here. Okay, now so since it's a uniform rod as mentioned in the question, we know that the weight will be acting downwards from the center. Okay, and since it's acting from the center, that means it's going to be 1.5 meters from each side. Here we go. Okay, now what we're supposed to do is we're supposed to show that the weight is equal to 490. Okay, now notice that we are given the tension in this string, which is 350 Newton, but we're not given the tension in this. Okay, so that means if, let's say, I pick this as the center, then we will have two unknowns. So not as the center, sorry. If I, let's say, resolve, or if I find out moments about C, then we will have to deal with weight and the tension, and they're both unknowns. So how about I pick a point and find moments from that, about that point, so that I don't have to deal with two unknowns. So let's pick A. Let's calculate moment about A. Okay, and remember, because it's in equilibrium, that means anticlockwise. Okay, all the forces acting anticlockwise, or all the moments acting anticlockwise, will be equal to the clockwise moments. Okay, and then what's moment? Moment is basically force into the perpendicular distance from that point, or from the point about which you are calculating moments. So let's first see all the moments that are acting in a clockwise direction and all the moments that are acting in a anti-clockwise. All the forces acting in a clockwise direction and all the forces acting in a anti-clockwise direction about A. Okay, so A is our center, so make sure you don't forget that. Now if you look at W, you can see W is a force that's acting in a clockwise direction, and if you look at 350, you can see 350 Newton is a force that's acting in an anti-clockwise direction. Okay, and we're talking about, we're basically using A as the fixed point. Okay, so anti-clockwise is equals to clockwise, so 350. Now the question is, what is the distance of this 350 Newton force from A? That is 2.1. So 2.1, this will be equal to the clockwise moment, and that is equal to W. Now be careful, what is the distance of W from A? The distance of W from A is 1.5. So W times 1.5. Now all we got to do is work this out. So let's work this out. 350 into 2.1 divided by 1.5, and yes, we do in fact get the value of W to be equal to 490 newtons, just as the question mentioned. So that's the answer to the first part. Let's mention it here. Now let's move to the next part. So as I mentioned, we're definitely going to use this diagram again. Here we are. Now let's have a look at part B. Let's see what it says. In fact, let me just paste part B here to save some time. Oops. Okay, now let's see what this says. So part B says a particle P of weight 210 newtons is attached to the rod at a distance d meters from A. Okay. Let's read the entire question first. The tension in the rope at C is now 600 Newton. Okay, so that means now the tension is 600. So here we go, 600. Okay. The rod remains in equilibrium in a horizontal position. Find the value of D. Okay. So First thing that you will notice is, yes, we know that the particle P of weight 210 Newton is attached and its distance from A is d meters, but we don't know whether d is greater than 2.1 or whether it's less than 2.1. Doesn't matter, okay? You can place it anywhere. It's not going to make a difference. Ultimately, you just have to make sure that you form a correct equation. Okay, so I don't know whether it's greater than 2.1, whether it's less than 2.1, but let's just say it's somewhere over here. Okay, we'll find out. Once we get the answer, we'll find out whether it's actually here or not. So at P, there is a force of 210 newtons. Okay, that's the weight basically. And don't forget that the weight is still acting from the center. And what's that equal to? That is equal to, we worked it out, 490. Yeah, 490 Newton. Now, once again, notice that we have to find out the value of d, and what's d? D is basically this distance. So I want to pick a point and calculate moment about that point so that we have only one unknown, and that's d. So once again, since we don't know what is the tension in this part of the string, so we will take moments about A. So taking moments about A, once again, all the clockwise moment was equal to the anti-clockwise moment. So if you look at 490, this is a force that's acting in a clockwise direction. This is also a force that's acting in a clockwise direction. The only force that's acting in an anti-clockwise direction is basically this one. Okay, so remember, anti-clockwise is equals to clockwise, or the other way around. So the only anti-clockwise force is 600, or you can say anti-clockwise moment. So 600 into 2.1 is equal to all the clockwise moments. So that would be 210 into d. Remember, we are basically calculating moment about A. So the distance is calculated, the perpendicular distance is calculated from the fixed point A. Plus 490 and 490, because it's a uniform rod, and as explained earlier, the weight will be acting right from the center, and the distance would be 1.5. So into 1.5. Now let's work this out. Let's see what do we get. This becomes 1260 is equals to 210d plus 735. So 210d is equals to 525, and we get the value of d to be equal to 2.5 meters. So our diagram where we mark d is incorrect. It's supposed to be somewhere over here. But anyway, like I said, there's the only way to find out is to actually work it out and then see what the value is. So that's the answer to part B. Now let's have a look at part C. Let's see what part C says. So once again, we're going to be using a fresh copy of the diagram given. Here is part C. Let's see what it says. So part C says that particle P is removed from the rod. All right. Particle Q of weight x newtons is now attached at P. Okay, so let's mark that. At B, we now have another particle, particle Q, and its weight is x newtons. Okay, now the rod remains in equilibrium in a horizontal position and is now on the point of tilting. Okay, interesting. So the rod is in equilibrium, but it's at the point of tilting. Now imagine that this rod is about to tilt. So if it's about to tilt, don't forget that there is the weight of the rod, which is still 490. Okay, there's tension here. Okay, and there's tension here. Okay, so this is tension A and this is tension in the string C. If the rod is about to tilt, I want you to pause and think for a minute. Will it go upwards or will it go downwards? Okay, the rod is hanging with the help of these two strings. Okay, and there's weight of the rod itself, and then there's another weight over here. Okay, so where do you think this rod will tilt? Well, if you think about it, this rod will obviously move in this direction. Okay, it's like if you've seen those divers. Okay, so the diver usually stands here. Okay, and as the diver starts jumping, we can see that the rod starts to move down. Okay, so it's kind of a similar situation over here. Now, if this rod moves down, so that means it's going to be perhaps something like this. Okay, and as it's something like this, that means this part of the string, this string itself will actually become slack. Okay, why? Because once it moves up, so that means there's no tension because it's slack, and since there's no tension, that means that's equal to 0. Okay, but there will be tension in this part of the string. Okay, as it moves down, there will be tension in this part of the string, but this part of this string will become slack. Okay, so that's very important for us to understand. Now, the weight is 1.5 meters. from A. Okay, we'll see whether we have to resolve, whether we have to find moments or calculate moments about A or C. We'll figure that out in a minute. First, let's mark all the distances. This distance will also be 1.5 since the length of the rod is 3 and the center, the weight is acting from the center. This would be equal to 2.1 minus 1.5, which is 0.6, and this would be equal to 1.5 minus 0.6, which is equal to 0.9. Now let's pick a point from where we're going to calculate moments. If I pick A, then what is the problem that we can run into? We'll have two unknowns. Okay, this force is unknown and this force is unknown. So how about I pick C? So if I pick C, then that means the distance of this force from C is 0. So we don't have to deal with this. And that will help us calculate the value of X. So let's calculate moments about C. Okay, and remember that tension at A is now equals to 0. And why is that? Because it's slack, as the question says, that it's on the point of tilting. It's not tilted yet, but it's on the point of tilting. So once again, clockwise is equals to anti-clockwise because it's still in equilibrium. So let's first mark all the forces that are acting. So let's first put a center here. Okay, so all the forces that are acting in an anti-clockwise direction. So that's 490. This is the force that's acting in an anti-clockwise direction. And this is a force that is acting in a clockwise direction. Yeah, it's acting in this direction. So this is the force that's acting in a clockwise direction. So anti-clockwise is equals to clockwise. Now 490 multiplied by the distance from C, that's 0.6, is equals to X multiplied by the distance, which is equal to 0.9. So work out the value of X using your calculator, obviously. So you will have 980 upon 3 newtons, which you can write in as a mixed number, which would be 326 whole 2 upon 3 newtons. And there you go. That's the answer to part C. And I hope it's clear to all of you.